Hello everybody. In this video we're going to start with the equimolar counter diffusion without chemical reaction, and we're going to follow the same procedure like before. We'll start with the governing equation, the continuity equation, and then apply the condition of equimolar counter diffusion and see how the concentration profile looks like and as we did in the case of the unidirectional diffusion. But before we go through these details, I want to go first in the details of the process, give an example of this process. So one of the very famous cases of equimolar counter diffusion in general is the distillation. So distillation is one of the separation processes where a mixture of two components is separated based on the difference in boiling point. So we have a more volatile component that evaporates at lower temperature and less volatile components that vaporize or evaporate at higher temperature. So when we put in a distillation column, when we put the liquid and vapor phases in contact with each other, where the two phases contain the two components, so I have A and B here and A and B here. So at the proper temperature and pressure, the more volatile component diffuses from the liquid phase to the vapor phase, and the less volatile component diffuses from the vapor phase to the liquid phase. So we have diffusion in opposite directions, one for the more volatile component and the other for the less volatile component. There are some cases where the fluxes are equal, so we have the number of moles per unit area for A going to the vapor phase equals to the number of moles of B going to the liquid phase per unit area. And this is what we call the equimolar counter diffusion. And in this case, we can say that the flux of A equals negative the flux of B, or flux of B equals negative the flux of A. So this is the main difference between the counter diffusion and the unidirectional molecular diffusion, because in case of unidirectional molecular diffusion, we said that NB equals to 0. But this is not the case here. N of NB is not equal to 0, it equals to negative N of A. So now when we go to the equations and see how we can represent this mathematically, we will start again with the same case. We have no reaction, we have a steady state, and for one-dimensional diffusion, then this is gonna be dNA by dZ equals 0, assuming that we have the diffusion in Z direction, and then this means that N is constant, and we will go for the second step, which is going to the flux. So in the flux equation, in this case we have NA equals negative NB, so this bracket would be cancelled out, and the flux equation is gonna be just the first term, which is negative D multiplied by dC by dZ. And then we can apply boundary conditions, any generic boundary conditions that at Z equals Z1, C equals CA1, and Z equals Z2, C equals CA2, just any normal conditions, and we can do the integration. We know from here that the flux is constant, so N is coming out of the integration. We do the integration of dZ from Z1 to Z2 and from dCA from CA1 to CA2, and of course we assume that the diffusivity is constant, assuming we have constant temperature and pressure, and that the diffusivity is not not affected much by the change in concentration between CA1 and CA2. This is a very, very simple and straightforward integration, which is going to be just delta C by delta L. And in case of ideal gas, we can use the equation in terms of pressure instead of concentration. So this is how the equation can be presented for gas phase or for partial pressures, and this is the equation that we can use for steady state equimolar counter diffusion. So it's more simpler than the case of unidirectional molecular diffusion. Again, this is valid, or this shape of the equation is different because this part of the equation is 0. So this can be due to the equimolar counter diffusion, where Na equals negative Nb, or when Ya is very, very small. And this is something we will visit at the end of this video, but I just want you to keep this in mind. If Ya is very, very small, then this term is going to be 0, and we will reach the same flux at the end. Now I want to go back to the film theory that assumes that the mass transfer takes place in very thin film that is at the surface of the liquid, and the thickness of this film is the distance where the mass transfer or the total mass transfer takes place. After this, there is no mass transfer, and as we increase the turbulence in the system, the thickness of the film decreases, and we were interested in finding the mass transfer coefficient based on the flux and the information that we know. So in this case, we can say that the flux is equals to the equimolar counter diffusion flux from this equation. We just put Z2 minus Z1 equals delta, which is the thickness of the film, and we said that this equals to Kc multiplied by the difference in concentration, or the Kc divided by RT multiplied by the difference in partial pressure. So from this we can, from this and this, we can tell that the mass transfer coefficient equal the diffusivity divided by delta, which is the thickness of the film. So this is, again, it's different from the form of the mass transfer coefficient for the same theory in case of unidirectional flow. Now let's see how the concentration profile will look like. So to get the concentration profile, we do integration, but instead of doing the integration as a limited integration, we do it as just normal integration. So this is the equation, which is negative d dCA by dZ. The differentiation of this equals 0, d equal constant, and this means that the second derivative of Ca is 0. If you integrate it twice, it's gonna be a linear relation that Ca equals Az plus B. And using the same boundary conditions that we used before, we will find that A equals Ca1 minus C2 divided by delta Z, Z1 minus Z2, and B equals Ca1 minus this slope multiplied by Z1. By substitution, we can find that this is the relation that we know for Ca with Z. Or we can put it in the dimensionless form where Z dash equals this difference, and this is a linear relation because this is Y. If it's Y equals AX plus B, then this is A, this is X, and this is B. So it's a linear relation between Ca and Z dash. If we want to plot it, then this is the profile. So if I start with 100% or one mole fraction, I mean concentration of 1 for A, then it's I mean for B from here, then it's going to be linear until the distance is done, and the opposite for A. So you have a linear relation for A and for B. This is the concentration profile. This is different from the case of the unidirectional flow where it was curved. So this is the last thing I want to mention in this in this video about the unidirectional flow. But I want to go back to one point that I mentioned earlier, which is the cases. This equation is going to be valid for Y is much smaller than 1, which means that the profile should be the same in case of Y equals a very small number, because it's the same condition. This equation is based on this integration differentiation, which is valid for the two cases. So if we try to use the unidirectional equation for YA equals 0.05, which is much smaller than 1, then this is the profile, which is a linear profile with distance. So this is it's also valid for or the linear profile is valid for Y is a very small number, and is valid for equimolar counter diffusion. So this is all for this video. So I'll end here, and in the next video we will start to deal with the case of chemical reactions, where it's not only diffusion, we have chemical reaction taking place. We will know what is the difference between homogeneous and heterogeneous reaction, and how we can deal with it mathematically using the continuity equation. So I'll see you then, inshallah. Goodbye.